the universe you can't see. Right now, as you're watching this video, you're swimming through dimensions you can't perceive. Not in some mystical New Age way, but according to some of the smartest physicists on the planet. And here's the kicker that'll blow your mind right off the bat. Everything you've ever seen, touched, or measured, every star in the night sky, every planet, every moon, every speck of cosmic dust, every atom in your body, all of it combined makes up less than 5% of the universe. That means 95% of reality is completely invisible to us. It's like we're fish trying to understand the ocean while being blind to water itself. Neil deGrasse Tyson, director of the Hayden Planetarium and one of America's most recognized astrophysicists, drives this point home in his narration of the Dark Universe exhibition at the American Museum of Natural History. We've sent robots to Mars, photographed black holes, detected gravitational waves from colliding neutron stars billions of light years away, and yet we're completely clueless about what constitutes the vast majority of existence. It's both terrifying and absolutely exhilarating. But it gets weirder. According to string theory, the leading candidate for a unified theory of physics, we're not just missing most of the universe's contents, we're also missing most of its dimensions. String theory suggests that reality has either 10 or 11 dimensions, not the measly 4 we experience every day. Charles Liu, the astrophysicist who co-authored the award-winning book One Universe at Home in the Cosmos with Tyson, has spent decades helping people wrap their heads around these mind-bending concepts. And trust me, once you understand what's really going on, you'll never look at empty space the same way again. If you're finding this fascinating so far, do me a favor and hit that subscribe button. We're about to dive deep into some seriously mind-blowing physics, and you won't want to miss what's coming up. The dark side of everything. Let's start with the elephant in the room, or should I say the invisible elephant that makes up most of the room. Dark matter and dark energy. These two mysterious entities account for roughly 95% of the universe we can't see, but they're completely different mysteries that both happen to share the word dark in their names. Dark matter makes up about 27% of the universe. We know it's there because galaxies spin way faster than they should, based on the visible matter we can see. Without something extra providing additional gravity, those galaxies would fly apart like a merry-go-round spinning too fast. When you add up all the stars, all the gas clouds, all the black holes, everything we can actually detect, 85% of the gravity in the universe is simply unaccounted for. It's like trying to balance your checkbook and realizing that most of your money is in an account you didn't know existed and can't access. Here's what makes dark matter so frustrating for physicists. It doesn't interact with light at all. It doesn't emit radiation. It doesn't absorb radiation. It doesn't reflect radiation. The only way we know it exists is through its gravitational effects on things we can see. Discovered by astronomer Fritz Zwicky back in 1933, when he noticed galaxy clusters moving strangely, dark matter has remained unsolved for over 90 years. Tyson calls it the longest standing problem in modern astrophysics. Tyson actually thinks we should rename it. He jokes that we should call it Fred, since the name dark matter implies we know it's matter, which we don't. His serious suggestion? Call it dark gravity instead, because what we're really measuring is unexplained gravitational effects. But dark matter stuck. So here we are, searching for something we can't see, don't understand, and can only detect indirectly. Dark energy. Now dark energy, that's even more bonkers. It makes up about 68% of the universe, and it's essentially a mysterious pressure in the vacuum of space that's causing the universe's expansion to accelerate. Empty space has pressure. The void itself is pushing outward, making galaxies fly apart from each other faster and faster. Einstein actually predicted something like this with his cosmological constant, a placeholder he added to his equations to explain why the universe wasn't collapsing under its own gravity. When Edwin Hubble discovered the universe was expanding in the late 1920s, Einstein supposedly called the constant his biggest blunder. But turns out he was right after all, just for different reasons than he thought. The implications are staggering. If this acceleration continues, and we have no reason to think it won't, the universe will eventually become a cold, dark, infinitely dispersed void. Every galaxy beyond our local group will eventually accelerate away from us, faster than the speed of light, disappearing beyond a cosmic horizon we'll never be able to cross. Future civilizations, trillions of years from now, if they exist, won't even be able to see other galaxies. They'll look up at the night sky and see nothing but darkness and their own local stars. Kind of makes you appreciate that we live in an era where we can still see the broader universe, doesn't it? String theory and the hidden dimensions. Alright, now let's talk about dimensions. Not the science fiction kind where you walk through a portal into an alternate reality, though honestly, the real thing is almost as weird. We live in what we perceive as a four-dimensional universe. 3 dimensions of space, length, width, height, and 1 dimension of time. You can move forward and backward, left and right, up and down, and inevitably, ceaselessly forward through time. That's our everyday experience of reality. But string theory says that's not the whole picture. According to the mathematics of string theory, space-time actually has either 10 or 11 dimensions total, depending on which version of the theory you're working with. The basic superstring theory requires 10 dimensions, while M theory, which unified different versions of string theory in the 1990s, requires 11. There's also an even earlier version called bosonic string theory that requires 26 dimensions, though most physicists don't take that one as seriously anymore because it predicts particles with imaginary mass, which doesn't make physical sense. Now I know what you're thinking. Where the heck are these extra dimensions hiding? Great question. This is where things get beautifully weird. Those extra dimensions are right where you're sitting, but they're curled up so incredibly small that we can't perceive them. We're talking about dimensions compactified down to about 1.6 times 10 to the negative 35 meters, which is the Planck length, the smallest possible meaningful distance in physics. Charles Liu uses a clever analogy to explain this. Imagine you're looking at a garden hose from far away. From a distance, the hose looks like a one-dimensional line stretching across your yard. But if you were an ant walking on that hose, you'd realize it's actually three-dimensional, with a circular cross-section that wraps around. That circular dimension was always there. You just couldn't see it from far away, because it was so small compared to the length. The extra dimensions of string theory work the same way, except way, way smaller. So small that even our most powerful particle accelerators can't probe down to those scales. These extra dimensions aren't just mathematical curiosities. They're absolutely essential to making string theory work. String theory proposes that all the fundamental particles in the universe, quarks, electrons, photons, everything, aren't actually point-like particles at all. They're tiny vibrating loops of energy, strings, oscillating at different frequencies. The way these strings vibrate determines what kind of particle they appear to be in our four-dimensional world, like how different vibrations of a guitar string produce different musical notes. But here's the thing. For the mathematics of string theory to be internally consistent, for the equations to work out without producing nonsensical infinities and contradictions, space-time needs to have exactly the right number of dimensions. It's not arbitrary. The number 10 or 11 falls directly out of the mathematical requirements of the theory itself. When physicists do the canonical quantization of the string, they find that certain particle states would have negative mass squared unless spacetime has exactly 10 dimensions for the superstring. Since negative mass squared isn't physically possible, the theory itself dictates how many dimensions must exist. Why you can't see higher dimensions. Tyson has a fantastic way of explaining our dimensional blindness using Edwin Abbott's book Flatland. Imagine you're a perfectly flat creature living on a sheet of paper. You can move forward and backward, left and right, but the concept of up doesn't exist in your universe. You can't even conceive of it. Now imagine a three-dimensional sphere passes through your two-dimensional world. From your perspective in Flatland, you'd see a circle that appears out of nowhere, grows larger, then shrinks and disappears. You wouldn't see the sphere as a sphere. You'd only see the two-dimensional cross-section of it intersecting your plane. The sphere would seem to have magical properties, appearing and disappearing at will, changing size mysteriously. We might be in the same situation with respect to higher dimensions. There could be higher dimensional objects passing through our three-dimensional space right now, and we'd only perceive their three-dimensional cross-sections. It's not that we're not smart enough to see these dimensions. It's that our senses are literally confined to 3 spatial dimensions, just like the Flatlanders are confined to 2. This has real implications for physics. Gravity follows an inverse square law because we live in 3 spatial dimensions. The gravitational field spreads out in all directions from a mass, and in 3 dimensions, the surface area of a sphere increases with the square of its radius. But if there were actually 9 spatial dimensions, like string theory suggests, then at very small scales, where those extra dimensions become relevant, gravity should follow an inverse 8th power law. Physicists are actively searching for deviations from the inverse square law at tiny distances to test whether these extra dimensions exist. So far, gravity follows the inverse square law down to distances of about 1/10 of a millimeter, which means if the extra dimensions exist, they must be curled up smaller than that. The Calabi-Yau manifold problem. Here's where string theory runs into a practical problem that makes physicists want to tear their hair out. Those extra 6 or 7 dimensions can't just be curled up any old way. They have to be wrapped up in very specific geometric shapes called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xingtung Yau. These are incredibly complex, higher dimensional shapes that satisfy certain mathematical properties required by string theory. Now, how many different Calabi-Yau manifolds are there? Estimates suggest something like 10 to the power of 500 different possible configurations. That's a 1 followed by 500 zeros, a number so stupendously large it's almost meaningless. And here's the problem. Each different Calabi-Yau manifold would give rise to a universe with different physical laws, different particles, different forces. This is what's called the landscape problem in string theory. The theory doesn't uniquely predict the universe we see. Instead, it predicts an almost infinite number of possible universes, each with its own physics, and we have no idea which Calabi-Yau manifold describes our universe. It's like having a theory that can predict any possible outcome, which means it doesn't really predict anything specific at all. This is one of the biggest criticisms of string theory, but here's what string theory has going for it. It's the only framework we have that naturally incorporates gravity into quantum mechanics. When you work out the mathematics of string theory, a massless spin 2 particle automatically appears that has all the right properties to be the graviton, the hypothetical quantum particle that carries the gravitational force. No other theory does this. String theory is also mathematically beautiful in a way that gives physicists goosebumps. Sometimes in physics, mathematical beauty has been a reliable guide to truth. General relativity was considered beautiful long before it was confirmed. The Higgs boson was predicted by beautiful mathematics decades before its discovery at CERN in 2012. When dimensions go quantum. Here's something that'll really bake your noodle. In quantum mechanics, the very concept of dimension might not be well defined at extremely small scales. Physicists working on M-theory have discovered something called T-duality, where a circular dimension of size L is mathematically equivalent to a circular dimension of size proportional to 1 over L. In other words, a really big circular dimension looks identical to a really tiny one in string theory. At the quantum level, you literally can't tell if a dimension is huge or tiny. This gets even stranger. When dimensions are curled up small enough, quantum effects become so strong that space-time itself starts to lose meaning. Just like how the surface of a pond looks smooth from far away, but reveals itself to be made of discrete water molecules up close, space-time might not be continuous all the way down. At the Planck scale, the concept of dimension itself might break down entirely, replaced by something more fundamental that we don't yet fully understand. Multiple dimensions of time. Now, let's really blow your mind. What if time had multiple dimensions? Charles Liu and Neil deGrasse Tyson have discussed on Star Talk what would happen if time had multiple dimensions, like space does. With multiple time dimensions, the past wouldn't be a single fixed sequence of events. There would be multiple past directions, multiple future directions, and the whole concept of causality, the idea that causes precede effects, would become incredibly complicated. You could have situations where event A causes event B in one time direction, but event B causes event A in another time direction. Most physicists don't think our universe has multiple time dimensions. The mathematics of physics seems to strongly prefer exactly one time dimension and multiple space dimensions. But why? Why is time so fundamentally different from space? We can move freely in all spatial directions, but we're stuck moving forward through time at a fixed rate. This asymmetry is one of the deepest mysteries in physics, and string theory doesn't really explain it. Living in the bulk. M-theory introduces an idea that sounds like pure science fiction. Our entire universe might be a three-dimensional membrane, or brain for short, floating in a higher dimensional space called the bulk. In this picture, all the particles and forces we know about, except gravity, are confined to our three-dimensional brain. But gravity is special. Gravitons can move through all 11 dimensions, including the bulk dimensions we can't access. This could explain why gravity is so much weaker than the other forces. Electromagnetism is about 10 to the 36 times stronger than gravity. The electromagnetic force binding electrons to atoms is strong enough that you can pick up a paperclip with a tiny refrigerator magnet, overcoming the gravitational pull of the entire Earth. The brain world scenario suggests gravity appears weak to us because most of its strength is diluted into extra dimensions we can't see. This raises a fascinating possibility. There could be other brains out there in the bulk, other three-dimensional universes with their own matter and energy, existing in the same higher dimensional space as ours, but separated by a tiny gap in the extra dimensions. We could never see them or interact with them, except possibly through gravity, which leaks between brains. Some versions of this idea even suggest that the Big Bang was the result of two brains colliding in the bulk. The search for evidence. So with all these mind-bending ideas, you might be wondering, is there any evidence for extra dimensions? The honest answer is no, not yet. The Large Hadron Collider has been looking for signs of extra dimensions by watching for particles that suddenly disappear during collisions, potentially escaping into extra dimensions. They've also searched for mini black holes, which some string theory models predict could be produced at high energies if extra dimensions exist. So far, nothing definitive. There are also indirect approaches, observations of how gravity behaves at different scales, measurements of the cosmic microwave background radiation, studies of dark matter and dark energy. All of these could potentially reveal hints of extra dimensions if we know what to look for. The problem is that the effects are predicted to be incredibly subtle, requiring extraordinary precision to detect. What it all means. Here's what gets me about all this. We're living in an era where we understand enough about physics to know that most of reality is hidden from us, but we don't yet understand enough to pierce through that veil. These ideas force us to confront how limited our perception of reality truly is. Everything you've ever experienced exists in a four-dimensional projection of a potentially 11-dimensional reality. And that 95% of the universe we can't see or understand? Dark matter and dark energy might be manifestations of physics happening in extra dimensions, or they might be entirely separate mysteries. We don't know. That's the thrilling and humbling part. After centuries of scientific progress, after splitting atoms and photographing black holes and detecting gravitational waves, we're still basically children trying to understand the universe. Charles Liu said something profound in his work. Galaxies are to the universe as cells are to the human body. If galaxies are the cells of the cosmos, then these hidden dimensions and dark components might be the DNA, the fundamental code underlying everything we see. And just like how discovering DNA revolutionized biology, understanding dark matter, dark energy, and extra dimensions might revolutionize our understanding of reality itself. The search continues with new experiments, more powerful telescopes, and more sensitive detectors. Maybe in our lifetimes, we'll get answers. Maybe it'll take centuries. Human curiosity and ingenuity have brought us this far. We've gone from thinking the Earth was flat to measuring the curvature of space-time itself. We've gone from believing Earth was the center of everything to understanding we're on a small planet orbiting an ordinary star in an unremarkable galaxy that's one of 2 trillion galaxies in the observable universe. So, are there hidden dimensions? Is 95% of the universe made of stuff we can't see? The evidence strongly suggests yes. The details? That's what makes this such an exciting time to be alive. We're living in the era when humanity might finally pull back the curtain and see what's really there. Thanks for watching, and keep looking up into all 11 dimensions.